universe is a vast and enigmatic expanse, filled with phenomena that continue to baffle even the most brilliant minds. From the earliest days of human civilization, our ancestors gazed up at the night sky, charting the stars and weaving stories about the constellations that glittered above. They saw the cosmos as a canvas of divine mystery, sparking questions that have persisted through the ages. As time unfolded, our understanding grew more sophisticated, evolving from mythology to empirical science. Yet the sense of wonder remained unchanged. Even today, with all the advances in space exploration and astronomical technology, the universe keeps its most profound secrets close, revealing only fragments of a much larger cosmic puzzle. Setting the scene, the awe-inspiring cosmos. Imagine standing beneath a clear sky, where the Milky Way stretches across the darkness in an ethereal band. We're merely a small part of this galactic ocean, orbiting a typical star on an ordinary spiral arm. And yet, our drive to understand the universe pushes us beyond our planetary boundaries, urging us to explore and question what lies beyond. This insatiable curiosity has fueled remarkable achievements: the landing on the moon, the breathtaking images captured by the Hubble Space Telescope, and the interstellar journey of probes like Voyager 1 and 2. Each milestone in space exploration has brought us closer to comprehending the cosmos, yet also revealed how much more remains unknown. The prospect of exploring one more star fits so closely into the imagination of space people like Voyager 1 and 2. This insatiable curiosity has brought us closer to comprehending the cosmos, yet also revealed how much more remains unknown. Each milestone in space exploration has brought us closer to comprehending the cosmos, yet also revealed how much more remains unknown. The human story of cosmic discovery. Our story of cosmic discovery is more than just a catalog of scientific milestones. It's a narrative interwoven with curiosity, ambition, and a relentless pursuit of knowledge. Consider the scientific revolution brought forth by pioneers like Galileo, who, with a simple telescope, forever changed our understanding of the heavens. Fast forward to today, and we have complex observatories like the James Webb Space Telescope probing the universe's deepest mysteries and providing data that continues to transform our understanding of cosmic phenomena. Introducing the cosmic anomalies. The essence of this journey lies in the anomalies, the peculiar, inexplicable features of our universe that challenge existing theories and open the door to new paradigms. These cosmic puzzles, from the invisible clutches of dark matter to the strange force of dark energy, are more than just scientific curiosities. They are reminders that the universe holds truths that lie beyond our current comprehension. Each anomaly hints at deeper, perhaps even revolutionary, principles yet to be discovered. These mysteries inspire scientists to build more sophisticated tools and to refine our models, fueling the engine of human progress. The philosophical and existential questions. Our exploration isn't just about uncovering data. It's a profound quest that bridges the realms of science and existential inquiry. Questions about the universe compel us to think about time, space, and existence itself, leading to discussions that border on the philosophical. What does the universe's true nature reveal about our place within it? Are we solitary observers in a lifeless void, or are there unknown civilizations waiting to be discovered? These questions, though vast, drive the spirit of scientific inquiry and influence our collective identity as a species. Brennbulb first found 1.3 billion years ago. In the interconnected nature of cosmic mysteries, the wonders of the universe are not isolated. They are deeply interconnected, forming a web of cosmic phenomena. Understanding one mystery often leads to revelations about another. For instance, studying the gravitational effects of dark matter has implications for understanding the structure of galaxies, just as the exploration of black holes has revealed the fundamental nature of space-time itself. It's a journey of continuous discovery, where every answer seems to generate new, tantalizing questions. Technology, our gateway to the cosmos. In this exploration, technology is our steadfast ally. It has enabled us to go beyond the limitations of our senses, revealing an invisible universe filled with wonders. Gravitational wave observatories allow us to hear cosmic collisions, while advanced satellites map the universe's oldest light. Yet even with all this ingenuity, we often find ourselves standing on the edge of the unknown, faced with phenomena that defy explanation. The universe, it seems, is a master of keeping secrets, the spirit of human exploration. Our quest for understanding is not just a scientific endeavor, it's a testament to the human spirit. It drives global collaboration, with astronomers, physicists, engineers, and thinkers from all walks of life working together to solve cosmic puzzles. It ignites the imagination of students, inspiring the next generation to reach for the stars. In a world divided by many differences, the cosmos offers a unifying narrative, an invitation to come together in pursuit of something greater. What to expect in this exploration? Throughout this script, we will delve deep into some of the most compelling mysteries that modern science is striving to unravel. From the elusive nature of dark matter and dark energy, to the puzzling properties of cosmic microwave background anomalies, we'll examine the evidence, theories, and cutting-edge research that drive the field of astrophysics forward. We'll also discuss the technological advances enabling these discoveries, and the profound impact these revelations have on our understanding of the universe and ourselves. Final thoughts and invitation to discover. Ultimately, our voyage into the cosmos is as much about understanding the universe as it is about understanding ourselves. Each anomaly, each question, and each theory remind us that we are a curious species, driven by a desire to learn and explore. As we venture deeper into this script, prepare to embark on a journey that spans galaxies, explores the fabric of reality, and touches the very edges of human knowledge. Welcome to the exploration of the greatest mysteries our universe has to offer. Transition from Introduction. The cosmos presents us with some of the most profound mysteries, challenging our understanding of physics and the very fabric of reality. As we move from a foundational exploration into these deeper complexities, we are confronted by a series of phenomena that remain elusive, yet fundamental to our comprehension of the universe. From the enigmatic nature of dark matter and dark energy to peculiar cosmic signals like the CMB anomalies, these mysteries push the limits of our knowledge and continue to inspire groundbreaking theories and experiments. The object further revealed itself. But why do these phenomena matter so deeply? Each discovery, or lack thereof, reshapes our theories about the universe's birth, evolution, and ultimate fate. The quest to understand these cosmic puzzles isn't merely an academic pursuit. It's a journey that could redefine our grasp of existence, inform our future technologies, and illuminate our place in the vast universe. Dark matter represents one of the greatest enigmas in modern astrophysics and cosmology. This mysterious substance is thought to make up around 27% of the universe's total mass energy content. To put this into perspective, ordinary matter, the kind that makes up stars, planets, and every object we see, accounts for only about 5%. The rest is dominated by dark energy, a separate and equally baffling phenomena. But what is dark matter, and why does it continue to puzzle scientists despite decades of research? The concept of dark matter dates back to the 1930s, when Swiss astronomer Fritz Zwicky observed the Coma cluster of galaxies. He found that galaxies within the cluster were moving so quickly that their gravitational interactions, based solely on visible mass, could not account for such high velocities. He proposed the existence of some unseen dark matter, providing the necessary gravitational pull. This idea was initially met with skepticism, but further evidence emerged in the 1970s, when astronomer Vera Rubin studied galaxy rotation curves. Rubin discovered that stars at the edges of galaxies were moving just as fast as those near the center, a phenomenon inconsistent with the distribution of visible matter. The gravitational influence of an invisible massive component was the only explanation. Fast forward to the present day, and the search for dark matter has intensified, leading to numerous hypotheses and experiments. One of the prevailing theories is that dark matter is composed of weakly interacting massive particles, WIMPs. These hypothetical particles would only interact with ordinary matter through gravity and the weak nuclear force, making them extremely difficult to detect. Several underground experiments, such as the Xenon 1T detector in Italy and the UX-Breckplin experiment in the United States, aim to capture these particles. These detectors are placed deep underground to shield them from cosmic rays and background radiation, hoping to observe the rare event of a WIMP interacting with a nucleus. Despite years of searching, no conclusive detection of WIMPs has been made, and the mystery persists. Alternative theories have been proposed to explain dark matter's elusive nature. Some scientists suggest that dark matter could be composed of axions, ultralight particles that could also help solve the strong CP problem in quantum chromodynamics. Others propose the existence of sterile neutrinos, a hypothetical type of neutrino that doesn't interact with ordinary matter or electromagnetic forces, but could contribute to the universe's mass. Still, others are exploring the possibility of modifications to our understanding of gravity itself, such as theories like modified Newtonian dynamics, MOND, or extensions to Einstein's general relativity. These theories suggest that our current models of gravity might not be entirely accurate on cosmological scales, but they face challenges in explaining all the observational evidence that supports the existence of dark matter. The indirect evidence for dark matter is compelling and comes from multiple independent sources. For example, gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity, occurs when massive objects like galaxy clusters bend the path of light from background objects. Observations of gravitational lensing show that the mass inferred from this bending far exceeds the visible mass of the lensing object, strongly implying the presence of dark matter. Additionally, studies of the cosmic microwave background (CMB) radiation, the afterglow of the Big Bang, revealed patterns that are best explained by the presence of dark matter in the early universe. The formation and distribution of large-scale structures, such as galaxies and galaxy clusters, also suggest that dark matter played a crucial role in shaping the universe we observe today. Beyond WIMPs and axions, dark matter might also exist in more exotic forms. One such idea is the existence of primordial black holes. These hypothetical black holes could have formed in the early universe from density fluctuations and might account for a portion of dark matter. Though intriguing, this theory raises more questions than answers, particularly regarding the precise mass distribution and observational constraints of these primordial black holes. Furthermore, the behavior of dark matter at various cosmic scales has profound implications for understanding the universe's past and future. At galactic scales, dark matter is believed to form halos around galaxies, providing the gravitational glue that keeps them from flying apart. These halos influence the way galaxies rotate and even the formation of new stars. At the cosmic scale, dark matter's role in the formation of the cosmic web, a vast network of interconnected filaments and voids, is crucial. Computer simulations that model the growth of the universe from the Big Bang to the present day show that without dark matter, the large-scale structures we observe today would not have formed. A natural conspiracy from deep space is doubtful by modern standards, but except by such filaments, an attempt to blend in, the large-scale structures we observe today would not have formed despite the overwhelming indirect evidence. One of the most frustrating aspects of dark matter research is the lack of direct detection. Theoretical physicists are constantly re-evaluating models, while experimentalists are refining their techniques. The Large Hadron Collider, LHC, at CERN, has been used to search for signs of dark matter particles being created in high-energy collisions. So far, these efforts have yet to yield definitive results, adding to the intrigue and frustration of the field. The quest to understand dark matter has led to numerous technological advancements and interdisciplinary collaborations. Instruments like the Fermi Gamma-ray Space Telescope and the Dark Energy Survey have provided invaluable data, even if they haven't directly revealed dark matter. Research into dark matter has also inspired the development of new mathematical models and computational techniques, some of which have applications beyond cosmology. Gregory Danger, Deepu. Magneto-photon madness. Confusing, manifesting physical properties. One of the most exciting aspects of dark matter research is its potential to revolutionize physics. If scientists can identify and understand dark matter, it could lead to groundbreaking discoveries in particle physics, cosmology, and beyond. Understanding dark matter might also have unforeseen technological applications, potentially influencing energy storage, material science, or even space exploration. The search for dark matter embodies the human spirit of curiosity and the desire to unravel the universe's secrets. However, the elusive nature of dark matter serves as a humbling reminder of how much we have yet to learn. It challenges our understanding of the universe and keeps scientists on the cutting edge of discovery. As we develop more sophisticated technology and refine our theoretical models, the hope remains that one day we will shed light on this dark cosmic mystery. Until then, dark matter continues to captivate our imagination and drive our quest for knowledge, remaining one of the most significant scientific challenges of our era. Dark energy is another profound and mysterious component of the universe, which, alongside dark matter, comprises roughly 95% of the total mass energy content of the cosmos. Unlike dark matter, which was proposed to explain the gravitational effects observed on large scales, dark energy was introduced to account for a surprising and seemingly paradoxical observation: the accelerated expansion of the universe. This discovery, made in the late 1990s, was a monumental shift in our understanding of the universe's behavior and destiny. But what exactly is dark energy? And how does it contribute to the structure and fate of the cosmos? The story of dark energy begins in the 1990s, when two independent teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, were studying Type I supernovae, a type of stellar explosion that occurs in binary systems. These supernovae are considered reliable standard candles for measuring astronomical distances because they have a consistent peak brightness. By observing the apparent brightness of these supernovae and measuring their redshift, a result of the expanding universe, they discovered that the farthest supernovae were dimmer than expected, indicating that they were farther away than previously thought. This observation was puzzling because it suggested that the universe was expanding at an accelerating rate rather than slowing down, as had been anticipated based on the assumption of gravitational attraction. The team's groundbreaking work led to the realization that a force was driving the accelerated expansion of the universe. This force, termed dark energy, was hypothesized to be a type of energy that permeates all of space, causing it to stretch and expand at an ever-increasing rate. Dark energy does not interact with matter in the same way as ordinary energy and does not produce detectable electromagnetic radiation. It is fundamentally different from both ordinary matter and dark matter, and as of now, it remains one of the most baffling aspects of cosmology. The concept of dark energy is supported by numerous observations and theoretical models. One key observation is the cosmic microwave background, CMB, radiation, which provides a snapshot of the universe as it was about 3.80000 Years after the Big Bang, analysis of the CMB's fluctuations reveals that the universe's geometry and expansion rate match predictions made by models that include dark energy. Additionally, the distribution of galaxies in large-scale surveys, such as the Sloan Digital Sky Survey, shows that the expansion of the universe has been accelerating over billions of years. The Gazette told her she had the winner prize. Several theoretical models have been proposed to explain the nature of dark energy. The simplest and most widely accepted explanation is that dark energy is a cosmological constant, denoted by the Greek letter lambda, introduced by Albert Einstein in his theory of general relativity. Einstein initially introduced the cosmological constant to maintain a static universe, but he discarded it after the discovery of the universe's expansion. However, with the discovery of cosmic acceleration, the cosmological constant was resurrected as a possible explanation for dark energy. In this model, dark energy is constant throughout space and time, and its effects are uniform throughout the universe. The cosmological constant model is supported by observations of the CMB and large-scale galaxy surveys, which suggest that the expansion rate of the universe is accelerating at a constant rate. However, this model leaves many questions unanswered. For instance, it fails to explain why the cosmological constant has such a small yet non-value value, which seems fine-tuned to match the current rate of cosmic expansion. This has led to a search for alternative explanations of dark energy. One such alternative is the idea of quintessence, a dynamic form of dark energy that evolves over time and can vary in different regions of the universe. Unlike the cosmological constant, which is fixed, quintessence allows for a more flexible model in which the equation of state of dark energy changes as the universe evolves. Quintessence models have been studied extensively in cosmology, and they are supported by some observational data, though they remain less widely accepted than the cosmological constant hypothesis. If quintessence exists, it would imply that the energy driving the acceleration of the universe's expansion could change in the future, potentially leading to different fates for the universe than those predicted by the cosmological constant model. End of note. Another explanation for dark energy comes from modifications to general relativity itself. Some physicists have suggested that our current understanding of gravity might be incomplete at cosmological scales. Modified gravity theories, such as FR gravity, propose that the gravitational force might behave differently on very large scales, which could account for the accelerated expansion of the universe without invoking dark energy as a separate component. These theories are still being tested against observations, and while they have some appeal, they do not yet offer a satisfactory alternative to dark energy. Despite the theoretical models and observational evidence, dark energy remains an enigmatic force, and its true nature is still unknown. The exact properties of dark energy could have profound implications for the ultimate fate of the universe. One possibility is that dark energy could continue to accelerate the expansion of the universe indefinitely, leading to a big freeze scenario in which galaxies, stars, and even atoms are eventually stretched apart to an unimaginable degree. Another possibility is that dark energy could change over time, eventually leading to a big crunch or a big rip. These potential scenarios depend on the nature of dark energy, which is still under intense scrutiny. One of the most exciting aspects of dark energy research is the possibility of testing its properties through future astronomical surveys and experiments. The European Space Agency's Euclid mission, scheduled for launch in the near future, aims to measure the expansion of the universe with unprecedented precision, allowing scientists to better understand the role of dark energy in shaping the cosmos. Similarly, the Vera C. Rubin Observatory, currently under construction in Chile, will conduct large-scale surveys of the universe to track the distribution of galaxies, and measure the effects of dark energy on cosmic expansion. Furthermore, gravitational wave astronomy, which has already provided groundbreaking insights into black hole mergers and neutron star collisions, could provide a new way to study dark energy. As gravitational wave detectors become more sensitive, it is possible that they will reveal new information about the expansion of the universe and the role of dark energy in accelerating it. It is very important to remember that the mathematical story of the universe and the role of dark energy in accelerating it. The study of dark energy is more than just an academic pursuit. It is a quest to understand the fundamental nature of the universe. Dark energy challenges our most basic assumptions about space, time, and the forces that govern them. The discovery of dark energy and the realization that the universe's expansion is accelerating has reshaped our understanding of cosmology and has opened up new avenues for exploration. While dark energy remains one of the biggest mysteries in science, it is also one of the most exciting frontiers. As technology advances and our observational tools become more sophisticated, scientists are optimistic that they will be able to unravel the secrets of this elusive force. The answers to the dark energy puzzle could have far-reaching implications, not only for cosmology, but also for fundamental physics, the fate of the universe, and our place within it. Cosmic Microwave Background, CMB. Anomalies. The cosmic microwave background, CMB, is one of the most important and profound pieces of evidence supporting the Big Bang theory of the universe. It is the faint glow of radiation that fills the universe and provides a snapshot of the cosmos when it was just 3,800,000 years old, offering a unique look at the early universe's conditions. However, while the CMB is often seen as a cornerstone of modern cosmology, it has also presented some intriguing anomalies that challenge our understanding of the universe's origins and structure. The CMB is essentially the afterglow of the Big Bang, a relic radiation that carries information about the early universe. When the universe was just a fraction of a second old, it was in a hot and dense state, filled with a plasma of charged particles. As the universe expanded and cooled, electrons and protons combined to form neutral hydrogen atoms, allowing photons, light particles, to travel freely through space. This released radiation, which we now detect as the CMB, is uniform across the sky in all directions, with a temperature of about 2.7 K, just above absolute zero. This near-perfect uniformity has been a critical piece of evidence for the Big Bang model, suggesting that the universe began from an extremely hot and dense state and has been expanding ever since. The useful contrast of such a dark background provides a strong interaction. However, upon closer inspection, scientists have noticed subtle variations in the CMB, known as temperature anisotropies. These temperature fluctuations, though minuscule, on the order of 1 part in 1,000,000, are crucial because they provide insight into the early universe's structure and evolution. They represent the seeds of galaxies, clusters, and other large-scale structures we see today. These fluctuations are believed to be caused by quantum fluctuations in the very early universe, amplified during a period of rapid expansion known as inflation. While these fluctuations are expected and well understood in the context of the Big Bang model, several anomalies in the CMB have raised questions and led to alternative theories. America before, from the point of view of people living in it, before experiencing the CMB, have been cited to support a sense of separation from inflation. These anomalies include unexpected patterns and asymmetries in the distribution of temperature fluctuations, which do not align perfectly with standard cosmological predictions. Some of these anomalies are subtle, while others are more striking and have sparked significant debate in the cosmological community. One of the most famous and debated CMB anomalies is the cold spot. The cold spot is an unusually large and cold region of the CMB that spans about 1.8 degrees on the sky, roughly the size of the full moon. This spot, which is about 100 microkelvins colder than the surrounding background radiation, was first detected by the WMAP, Wilkinson satellite, and later confirmed by the Planck satellite. Its existence is puzzling because, according to the standard model of cosmology, there is no clear explanation for why such a large and cold patch of the universe should exist. The cold spot has led to several hypotheses. One possibility is that it is a remnant of an ancient supervoid, a vast, nearly empty region of space where the density of matter is extremely low. According to this hypothesis, the cold spot could be the result of the gravitational effects of this supervoid, which would cause the CMB radiation passing through it to be stretched and redshifted, making it appear colder than it should be. However, this explanation is not universally accepted, and some researchers have questioned whether such a large supervoid could exist in the first place. Another, more speculative explanation is that the cold spot could be evidence of a collision with another universe in a multiverse scenario. According to some models of cosmic inflation, our universe could be just one bubble in a much larger multiverse, where each bubble has its own distinct physical properties. If two such bubbles were to collide, the resulting interaction could create anomalies in the CMB, including the cold spot. This idea, though intriguing, is highly speculative and remains far from being proven. In addition to the cold spot, another significant anomaly in the CMB is the axis of evil. The axis of evil refers to an alignment of the large-scale temperature anisotropies in the sky. This axis is not expected according to the standard cosmological model, which predicts that the distribution of temperature fluctuations should be statistically isotropic, that is, the same in all directions. The discovery of the axis of evil raises questions about the fundamental symmetries of the universe and has led to various interpretations, including the possibility that the universe is not as homogeneous and isotropic as previously thought. Some researchers suggest that the axis of evil could be a statistical fluke or an artifact of the data. However, others have argued that it could indicate new physics, such as deviations from the cosmological principle, which posits that the universe is homogeneous and isotropic on large scales, or a sign of gravitational effects from a large-scale structure, such as a supercluster of galaxies, influencing the CMB. Another anomaly worth mentioning is the multipole moment anomaly, which involves irregularities in the distribution of temperature fluctuations across different angular scales. In particular, the dipole moment, the difference between the hottest and coldest regions, is larger than expected in the standard cosmological model. This could point to a need for new physics or indicate that the universe's geometry is different from what we expect, possibly hinting at the presence of large-scale structures or even fundamental flaws in our understanding of cosmology. These anomalies in the CMB are not just curiosities. They have important implications for the foundations of cosmology. The fact that these anomalies have been detected with high precision suggests that we may need to revise our current models of the universe. Some scientists have even proposed that these existential scientific models could point to the existence of hidden dimensions, alternative models of inflation, or variations in the laws of physics over time. Moreover, these anomalies challenge our understanding of the Big Bang model and the inflationary period that followed it. The theory of inflation suggests that the universe underwent a rapid and exponential expansion in the first moments after the Big Bang, smoothing out any irregularities. However, if significant asymmetries or large-scale anomalies exist, this challenges the idea that the universe was entirely uniform at the start, as inflation theory would predict. Future observations and missions will be crucial in resolving these anomalies and providing a clearer picture of the early universe. The James Webb Space Telescope, JWST, which will provide unprecedented observations in the infrared spectrum, could offer new insights into the CMB and the early universe. Additionally, the European Space Agency's Planck satellite has already provided detailed measurements of the CMB, but future surveys with even more advanced instruments could help clarify the nature of these anomalies and whether they represent new physics or are simply statistical artifacts. In conclusion, the cosmic microwave background remains one of the most vital tools for understanding the origins of the universe. However, the anomalies detected in its radiation pose significant challenges and could revolutionize our understanding of cosmology if they are confirmed and explained. Whether these anomalies represent new physics, observational errors, or the result of large-scale structures is still up for debate. But they undoubtedly serve as a powerful reminder that the universe continues to surprise us with its mysteries. The study of the CMB will remain a cornerstone of cosmological research for years to come, providing both answers and new questions as we explore the vastness of the cosmos. Quasars, short for quasi-stellar objects, are among the most fascinating and extreme phenomena in the universe. Discovered in the early 1960s, quasars are incredibly bright and distant objects that resemble stars in the sky but have properties unlike anything seen in our Milky Way. Pierced by the study of quasars has revolutionized our understanding of the universe, providing key insights into the early cosmos, the growth of supermassive black holes, and the mysteries of high-energy astrophysics. At their core, quasars are powered by supermassive black holes located at the centers of galaxies. These black holes, with masses millions to billions of times that of the Sun, are surrounded by vast accretion disks of gas, dust, and other material that swirl in toward the black hole due to its immense gravitational pull. As the material in the accretion disk spirals inward, it heats up to incredibly high temperatures, emitting vast amounts of energy in the form of electromagnetic radiation. This radiation can outshine the combined light of all the stars in the host galaxy, making quasars among the brightest objects in the universe. "Rads," said Simon. "Rads." The energy released by quasars spans the entire electromagnetic spectrum, from radio waves to X-rays, with some quasars emitting jets of relativistic particles that extend vast distances into space. These jets are often aligned with the quasar's rotational axis, and their energy can be so intense that they affect the surrounding intergalactic medium, influencing galaxy formation and evolution. One of the most intriguing aspects of quasars is their incredible distance from Earth. Quasars are typically found billions of light years away, meaning that the light we observe from them was emitted when the universe was much younger, just a few 100 million years after the Big Bang. This makes quasars invaluable tools for studying the early universe and understanding the conditions that existed shortly after its formation. The discovery of quasars in the 1960s opened up a new window into the distant past, providing a glimpse into the formation of galaxies, black holes, and the evolution of the universe. However, despite decades of study, quasars continue to present several anomalies that challenge our understanding of astrophysics. One of the most puzzling aspects of quasars is their immense luminosity. The fact that a single supermassive black hole can produce such extraordinary amounts of energy from a relatively small region of space is still not fully understood. Some researchers have suggested that quasars might be powered not just by the accretion of material into the black hole, but also by other processes, such as the formation of magnetic fields, or interactions between the black hole and the surrounding environment. These alternative explanations are still speculative, and more data is needed to confirm or refute them. Another anomaly associated with quasars is the phenomenon known as redshift. Redshift refers to the stretching of light waves as they travel through space, which occurs due to the expansion of the universe. The greater the distance between an object and the observer, the more its light is redshifted. This is a key piece of evidence supporting the Big Bang theory and the expanding universe. However, quasars exhibit anomalous redshifts, meaning that some quasars have been observed to have redshifts that do not fit the expected patterns based on the known expansion of the universe. This has led to various hypotheses, including the possibility of non-standard cosmological models or errors in the measurement of redshift. In addition to redshift anomalies, quasars also exhibit variations in their brightness over time, sometimes on very short timescales. These fluctuations can be quite dramatic, with a quasar's brightness changing by factors of 10 or more in a matter of days or weeks. This rapid variability challenges our understanding of the processes at work within quasars. The fact that the brightness of a quasar can change so quickly suggests that the emitting region must be incredibly small, perhaps only a few light days or light weeks across. Since light travels at a finite speed, this implies that the region must be compact with very high energy densities. The source of these variations is still a subject of active research, with possible explanations ranging from instabilities in the accretion disk to the behavior of the relativistic jets. Another fascinating anomaly of quasars is their superluminal motion. In some cases, quasars have been observed to exhibit apparent superluminal motion in their jets, meaning that the material in the jets appears to be moving faster than the speed of light. This seems to violate one of the fundamental laws of physics, but in reality the effect is an optical illusion caused by the angle at which we observe the jets. And the jets are moving almost directly toward or away from the observer. The motion appears faster than the speed of light due to the relativistic Doppler effect. However, this phenomenon does not actually violate any laws of physics, as it does not involve the actual motion of material faster than the speed of light. Quasars also challenge our understanding of the growth of supermassive black holes. In some cases, the supermassive black holes at the centers of quasars seem to have formed incredibly quickly, reaching enormous masses in just a few 100 million years. This rapid growth is difficult to reconcile with the standard models of black hole formation, which suggests that black holes grow more gradually over billions of years. Next among the things we hardly expect to find on the ground is a massive black hole. One hypothesis is that the first supermassive black holes could have formed from the collapse of massive primordial gas clouds in the early universe. But this idea remains speculative, and further observations are needed to confirm it. Finally, quasars are also involved in some of the most extreme gravitational phenomena observed in the universe. The intense gravitational fields around supermassive black holes can bend and distort light, a phenomenon known as gravitational lensing. Quasars are often found at the center of galaxy clusters, where the gravitational lensing effects can magnify and distort the light from the quasar, allowing us to study these distant objects in greater detail. This phenomenon also provides a unique opportunity to test the predictions of general relativity in extreme conditions. In conclusion, quasars are among the most fascinating and enigmatic objects in the universe. Their extreme brightness, vast distances, and strange behavior challenge our understanding of astrophysics and cosmology. While we have made great strides in studying quasars, many questions remain, particularly regarding the exact mechanisms behind their immense energy output, rapid variability, and other anomalous behaviors. Continued observations and advancements in technology will likely provide more answers, but quasars are sure to remain a central mystery in the study of the universe for the foreseeable future. In 2017, the discovery of an object from outside our solar system ignited one of the most intriguing debates in modern astronomy. The object, named Oumuamua, Hawaiian for scout or messenger, was an interstellar visitor that passed through our solar system. and its unusual characteristics have left scientists puzzled ever since. The mystery surrounding Oumuamua highlights the potential for unexpected discoveries in the vast, unexplored reaches of space. Oumuamua was first detected on October 19, 2017, by astronomers using the Pan-STAR 1 telescope in Hawaii. It was initially thought to be a comet, but its strange motion quickly raised suspicions. Unlike comets, which typically exhibit a visible coma and tail as they approach the sun, Oumuamua displayed no such features. Despite this, its high velocity and trajectory suggested that it was not native to our solar system, but rather an object that had traveled across interstellar space for millions, if not billions of years. Impossible to say entirely. The object's origin, trajectory, and unusual behavior sparked a flurry of interest among astronomers, who soon realized that Oumuamua was unlike anything they had ever encountered. It was confirmed to be an interstellar object, meaning it came from another star system. This made it the first known object to enter our solar system from interstellar space, opening up an entirely new area of study for astronomers and astrophysicists. One of the most perplexing aspects of Oumuamua is its highly elongated shape. Early observations suggested that the object was about 800 meters long, but only around 80 meters wide, resembling a cigar or needle-like shape. This highly unusual form, combined with its rapid rotation, led some researchers to speculate about its composition. The shape and rotation were inconsistent with the typical characteristics of known asteroids or comets. Its rapid spinning at a rate of once every 7.3 hours was particularly puzzling. This behavior led scientists to wonder if the object was a fragment of a larger object, possibly broken off from a larger body, or if it had been artificially constructed. Another anomaly of Oumuamua's behavior was its acceleration as it passed through the solar system. As it traveled towards the sun, astronomers noticed that it was moving faster than expected, based on the gravitational influence of the sun alone. This was not typical of ordinary asteroids or comets, which usually follow predictable paths, influenced solely by gravity. The additional acceleration suggested that some other force was at play, one that could not be explained by standard gravitational mechanics. The lack of a visible tail or coma, which is characteristic of comets, led to one of the most widely discussed theories surrounding Oumuamua, that it might be an artificial object. This idea was proposed by researchers like Avi Loeb, a professor of science at Harvard University, who suggested that Oumuamua could be a probe sent by an alien civilization. Loeb argued that the acceleration of Oumuamua could have been caused by radiation pressure from the sun, pushing on a thin, flat object like a solar sail. According to this hypothesis, Oumuamua might be a probe deliberately sent toward our solar system, although this idea remains speculative and controversial. Critics argue that the data does not support this interpretation, and many researchers believe that natural explanations are more likely. One such natural explanation involves the possibility that Oumuamua could be a fragment of a larger body that was ejected from a distant star system. Some have speculated that the object could have once been part of a comet or asteroid, but due to the high-speed impact with another object or an unusual encounter with a nearby star, it was broken off and sent on its interstellar journey. In this scenario, the object's odd acceleration could be explained by the outgassing of volatile material from the surface, which would create a push similar to a rocket engine. However, the lack of any visible signs of outgassing makes this explanation less convincing. Point 2. The shape of Oumuamua also continues to be a subject of debate. Its long, thin form, combined with its rapid rotation, has led some researchers to suggest that it could be a fragment of a shattered comet or asteroid. The object's unusual rotation might be the result of internal stress or an uneven distribution of mass within the object, possibly due to the gravitational forces it encountered in its journey across the galaxy. Another theory posits that the object could be a hydrogen iceberg, a chunk of frozen hydrogen from an exoplanet that was ejected into space. The ice could sublimate as the object approached the sun, causing the acceleration observed. But again, no direct evidence for this hypothesis has been found. One of the most perplexing aspects of Oumuamua is the lack of definitive data. Unlike typical objects in the solar system, Oumuamua was observed from a great distance and only for a limited time before it passed beyond the reach of our telescopes. This means that much of the data collected about the object is inconclusive, and many of the theories put forward are based on limited observations. Scientists have pointed out that had Oumuamua been observed for a longer period, it might have been possible to discern more about its composition, structure, and behavior, leading to more concrete answers. Despite the controversies and unanswered questions surrounding Oumuamua, the object has opened up an entirely new avenue of scientific inquiry. Its unexpected appearance in our solar system has sparked interest in the possibility of other interstellar objects that could be out there, waiting to be discovered. Oumuamua's strange characteristics have led to a greater awareness of the types of objects that could exist beyond our solar system, and future observations may lead to the discovery of more objects like it. In fact, astronomers are already on the lookout for other interstellar visitors, and the discovery of another Oumuamua-like object could provide crucial insights into the nature of these interstellar travelers. The mystery of Oumuamua highlights the complexities of studying the cosmos, where unexpected phenomena can challenge our understanding of the universe. Whether it is a natural object, an artificial probe, or something entirely different, Oumuamua's journey through the solar system has added a new chapter to the story of our exploration of space. This once-upon-a-time civilian crew member, now running a company, and running it as a publicly traded company. As technology improves and our ability to observe distant objects grows, more objects from outside our solar system will likely be discovered, potentially revealing even more about the mysteries of the cosmos. Rogue planets. Rogue planets, also known as interstellar or nomadic planets, are one of the most intriguing and mysterious anomalies in modern astronomy. These planets, which are not bound to any star, wander through the galaxy alone, without the gravitational anchor of a host star. Their existence challenges traditional views about planetary formation and the behavior of planetary systems. Typically, planets are considered to be objects that orbit stars. In fact, the very definition of a planet is often tied to the idea that it resides in the orbit of a star. However, rogue planets defy this conventional model, as they have been ejected from their original star systems or formed independently in the cold depths of space. Moons and planets can spring from the cold depths of space. It is believed that rogue planets make up a significant portion of the planetary population in our galaxy. Though their elusive nature makes them difficult to study, the discovery of rogue planets is relatively recent. For many years, astronomers theorized that they existed, but evidence for their existence only began to emerge with the advent of more advanced observational techniques. Still, rogue planets were first detected indirectly through their gravitational effects on other objects, and later through direct imaging and infrared observations. One of the most compelling aspects of rogue planets is the mystery surrounding their formation. There are two primary theories regarding how these planets come into being. They can either form in isolation or be ejected from their parent star system. In the first scenario, rogue planets are thought to form in the dark nebula or molecular clouds, vast cold regions of space where gas and dust condense to form stars and planets. Some scientists speculate that rogue planets might form as independently orbiting bodies within these clouds, never gravitationally bound to a star. This theory challenges the traditional idea that planets must always form in the vicinity of a star, potentially providing a new avenue for understanding planet formation in the broader universe. Alternatively, rogue planets can be ejected from their parent star system. This process can occur in a number of ways, such as through gravitational interactions with other massive bodies within the system. If a planet's orbit becomes unstable, perhaps due to a close encounter with a giant planet or the influence of a passing star, it can be ejected from its system and sent into the depths of interstellar space. This scenario is thought to be the most common pathway for rogue planet formation. A study in 2018 estimated that there could be as many as 1,000,000 times more rogue planets than stars in our galaxy. If true, this would mean that the Milky Way is teeming with planets that are completely free from the influence of any star. If that's the case, it will be hard to imagine a world habitable by life, and that supplying energy to Earth is like something the Genii have never seen. One of the most fascinating features of rogue planets is that, despite their isolation from any star, they might still harbor some form of heat. This heat does not come from the warmth of a nearby star, but from the residual heat left over from the planet's formation. Young rogue planets, for instance, can still possess enough internal heat to glow in the infrared telescopes, which have been instrumental in discovering rogue planets. Hence, the Moondash actress's description represents the choralities of the loads of which Earth and Saturn. This residual heat, combined with the lack of sunlight, makes these planets incredibly cold, with surface temperatures plunging to hundreds of degrees below freezing. The idea of a rogue planet traveling through the galaxy without a star also raises questions about the possibility of life. While the chances of life as we know it are slim on a rogue planet, due to the lack of solar radiation, heat, and warmth, some researchers have speculated that life could potentially exist in other forms, adapted to the extreme cold. This is a topic of active debate and research, particularly in the search for exoplanets that might support life. Could a rogue planet have the right conditions for life to arise and survive in the frozen depths of space? While the odds are low, the idea that life could exist on a rogue planet opens up new possibilities in astrobiology. A flying car is a horrible idea. Rogue planets also challenge our understanding of planetary systems. In traditional planetary systems, planets are bound to stars by gravity. However, rogue planets operate outside this model. If rogue planets were once part of a star system, their ejection raises questions about the stability of planetary orbits and the dynamics of star systems. How can planets be ejected, and what does this mean for the future of solar systems? Is it possible that our own planet could one day be ejected from the Sun's orbit, or that a rogue planet could collide with our solar system in the distant future? Interestingly, there are also examples of rogue planets being captured by other stars. When a rogue planet passes close enough to a star, the gravitational pull of that star can capture it and add it to the star's planetary system. This process is extremely rare, but has been theorized as a possible outcome for rogue planets in the long term. The capture of a rogue planet could lead to the formation of new planetary systems or the rearrangement of existing ones. Despite the theoretical predictions and indirect evidence, direct observation of rogue planets remains challenging. Their lack of a host star makes them extremely difficult to spot with traditional observational techniques, which are typically designed to detect planets in orbit around stars. However, advancements in technology and observational methods, such as infrared imaging, are slowly increasing our ability to detect and study these mysterious objects. In the future, upcoming space telescopes like the James Webb Space Telescope may significantly improve our ability to identify and study rogue planets, providing more insight into their origins and characteristics. Rogue planets represent one of the most intriguing and enigmatic phenomena in the cosmos. Their existence forces us to rethink traditional models of planetary formation and behavior. Whether formed independently in the depths of molecular clouds or ejected from their parent star systems, rogue planets continue to challenge our understanding of the universe. their potential for harboring life, their unique properties, and their role in planetary dynamics are just a few of the many reasons why they are a focal point for ongoing astronomical research. As we continue to explore the galaxy and improve our technology, rogue planets may offer new opportunities to unlock the secrets of planetary formation, evolution, and the potential for life beyond the confines of our sun. They represent a frontier of discovery, one that pushes the boundaries of our understanding and offers exciting new possibilities for the future of space exploration. Wormholes, sometimes referred to as Einstein-Rosen bridges, are one of the most fascinating and perplexing theoretical concepts in physics. They are hypothetical structures in space-time that act as shortcuts or tunnels between distant points in the universe. While their existence is not confirmed, the possibility of wormholes challenges our understanding of space, time, and gravity, and opens the door to discussions about interstellar travel, the nature of the universe, and even time travel. A wormhole is, in essence, a passage through space-time that could, in theory, allow an object to travel from one point in space to another, bypassing the intervening space. Imagine a piece of paper with two holes punched in it. If you fold the paper so that the two holes line up, the distance between them is instantaneously reduced to the thickness of the paper. In this analogy, the paper represents the fabric of space-time, and the holes represent different points in the universe. A wormhole would therefore be a shortcut through this fabric of space-time, potentially allowing travel between distant regions of the universe in a fraction of the time it would take using conventional means. The concept of a wormhole was first proposed by Albert Einstein and his colleague Nathan Rosen in 1935 as part of their work on the theory of general relativity. They theorized that a wormhole could form from a black hole and that the mouth of the black hole could lead to another point in space-time. These theoretical structures became known as Einstein-Rosen bridges. According to general relativity, a black hole is a region of space-time where gravity is so intense that not even light can escape. If a wormhole were connected to a black hole, it could theoretically act as a shortcut to other regions of space or even time. Despite the intriguing possibility of wormholes, there are several significant challenges that need to be addressed before they can be considered viable structures. The most critical issue is the concept of exotic matter, the type of matter that would be required to keep a wormhole open. Without exotic matter, the wormhole would collapse under its own gravity, and the passage would close before anything could travel through it. In other words, any attempt to traverse the wormhole would be thwarted before it even began. Exotic matter is a theoretical form of matter that would have negative energy density and negative pressure, which is the opposite of ordinary matter. This type of matter is not something we have observed in nature, but it is mathematically predicted to be required for a stable wormhole. Even if exotic matter were to exist, there is no guarantee that wormholes could be traversed by humans or other objects. The intense gravitational forces near a wormhole's entrance, especially near a black hole, could cause extreme tidal forces, potentially ripping apart anything attempting to pass through. Moreover, the time dilation effects near a black hole would be profound, meaning that time would pass differently for someone inside the wormhole compared to an observer outside. These challenges make the practical use of wormholes for travel extremely uncertain, and the idea remains largely speculative. Despite these challenges, the concept of wormholes has captured the imagination of physicists, astronomers, and science fiction writers alike. In science fiction, wormholes are often depicted as shortcuts for spaceships to travel vast distances in the universe, or as time machines that allow for travel into the past or future. While these ideas remain firmly in the realm of fiction, they are based on the same theoretical principles proposed by general relativity. And some scientists believe that, given enough time and technological advancement, it might be possible to harness the properties of wormholes for practical purposes. One of the most intriguing possibilities of wormholes is their potential to serve as a means of faster-than-light travel. The speed of light is the ultimate speed limit in our universe, according to the theory of relativity. However, if a wormhole could be created that connects two distant points in space, an object could theoretically travel from one point to another instantaneously, bypassing the light speed limit. This opens up tantalizing possibilities for space exploration, as it could potentially allow humanity to visit distant stars and galaxies in a matter of days or even seconds, rather than the centuries or millennia it would take using conventional spacecraft. However, wormholes may not only offer shortcuts through space, but also through time. Some theories suggest that it may be possible for a wormhole to act as a time machine, allowing for travel to the past or the future. This is where things get particularly complex and speculative. According to general relativity, time and space are interconnected and form what is known as space-time. In this framework, wormholes could potentially create loops in space-time that allow for time travel. The idea is that if a wormhole were to connect 2 points in time, say, one in the distant past and one in the future, it could allow an object to travel between those points. However, the implications of time travel via wormholes are profound and create paradoxes that challenge our understanding of causality. One well-known example is the grandfather paradox, the hypothetical situation where a time traveler goes back in time and prevents their own grandfather from meeting their grandmother, thereby preventing their own birth. This paradox raises the question of whether time travel is logically consistent and whether it is possible to change the past. Some physicists have proposed that the universe may have built-in mechanisms to prevent such paradoxes, such as the idea of self-consistency, which suggests that any event that could alter the past would necessarily already have been accounted for in the present. Another challenge associated with wormholes and time travel is the possibility of time loops. If wormholes connect 2 points in time, it could lead to a situation where events in the future could influence or even cause events in the past, creating a feedback loop. This raises the question of whether the future can influence the past and whether such loops would be stable or lead to contradictions. In addition to theoretical discussions, recent advances in quantum mechanics and string theory have provided new insights into the nature of space-time and wormholes. According to quantum theory, space-time is not a smooth, continuous fabric, but is instead made up of discrete units. This has led to new models of wormholes that suggest they may be connected to the fundamental nature of space itself. Some researchers have suggested that wormholes could be created in the fabric of quantum space-time, potentially allowing for the creation of stable, traversable wormholes. However, much more research is needed before we can determine whether this is a feasible possibility. Despite the many challenges and unanswered questions, the concept of wormholes remains one of the most tantalizing ideas in modern physics. They are an elegant and mysterious feature of the universe that may hold the key to unlocking the secrets of space-time, gravity, and even time itself. While we are far from being able to harness wormholes for practical use, they represent a frontier of scientific discovery, an anomaly that may one day offer profound insights into the very nature of the universe. Technology and innovations in space exploration. Space exploration has been propelled forward by incredible advancements in technology, enabling humans to venture beyond Earth's atmosphere and gain profound insights into the universe. This section delves into some of the most critical technologies that have shaped space exploration, with a focus on the tools, methods, and innovations that have expanded the boundaries of our understanding. These technologies not only help us gather data from distant corners of the universe, but also offer solutions to the various anomalies and questions posed by space, which we will examine in the following sections. Rockets and propulsion technologies. At the heart of space exploration are the rockets and propulsion systems that make space travel possible. The development of reliable rockets began in the mid-20th century, with early innovations laying the groundwork for manned and unmanned missions. The Saturn V rocket, for example, was a monumental achievement that carried astronauts to the moon during the Apollo missions. These rockets provided the initial leap to break free from Earth's gravity. Over the decades, rocket technology has advanced significantly. While chemical rockets remain the mainstay for space launches, recent breakthroughs have introduced new, more efficient propulsion systems. Ion propulsion, which uses charged particles to generate thrust, offers a much more fuel-efficient method of propulsion, enabling missions that would otherwise be impossible due to fuel constraints. More recent research points to a much more fuel-efficient method of propulsion system. The Dawn spacecraft was a prime example of ion propulsion in action, providing unprecedented exploration of the asteroid belt. The potential of ion propulsion will be crucial for missions to Mars and other distant planets. Looking further into the future, nuclear propulsion holds promise for deep space exploration, with its potential for faster travel and greater efficiency. Nuclear thermal propulsion, NTP, and nuclear electric propulsion, NEP, are two promising technologies that could allow missions to reach distant destinations, like the outer planets and even interstellar space, more swiftly. Space telescopes and observational instruments. Another revolutionary leap in space exploration was the development of space telescopes. Unlike ground-based telescopes, which are limited by Earth's atmosphere, space telescopes offer a clear, uninterrupted view of the universe. The Hubble Space Telescope, launched in 1990, has provided some of the most iconic images of the cosmos. From distant galaxies to nebulae, these observations have not only expanded our understanding of the universe's structure and evolution, but have also given scientists the tools to study the unexplained phenomena like dark matter and dark energy in greater detail. The James Webb Space Telescope, launched in 2021, is the next step in this journey. With its advanced instruments designed to study infrared light, JWST promises to uncover new insights into the formation of galaxies, stars, and planetary systems. It will also provide critical data for understanding the fundamental mysteries of the universe, such as the behavior of dark energy and the early conditions of the universe. Robotic spacecraft and rovers. Robotic spacecraft and rovers are essential for exploring other planets and moons. These unmanned explorers have given us detailed images of planetary surfaces and have provided insights into the potential for life beyond Earth. The most famous of these are the Mars rovers, including Spirit, Opportunity, Curiosity, and Perseverance. Each of these rovers has contributed critical information about Mars's geology, atmosphere, and history. For example, Curiosity made headlines with its discovery of ancient water on Mars, raising the possibility that the red planet may have once harbored microbial life. Perseverance, launched in 2020, is equipped with advanced instruments to search for signs of past life and collect samples that will eventually be returned to Earth. In addition to Mars, robotic spacecraft have been sent to study other parts of the solar system. The Voyager missions have traveled beyond our solar system, providing humanity's first glimpses of interstellar space. New Horizons, which flew by Pluto in 2015, delivered the first close-up images of the dwarf planet, opening a new chapter in our understanding of the outer solar system. Space stations and future habitats. Human space exploration has also been significantly advanced by the development of space stations. The International Space Station, ISS, which has been orbiting Earth since 1998, serves as both a research platform and a testing ground for technologies needed for future deep space missions. The ISS has been instrumental in studying the effects of microgravity on human health and other celestial bodies. NASA's Artemis program aims to return humans to the moon, with the ultimate goal of establishing a sustainable human presence there. This requires developing space habitats capable of supporting life for extended periods. 3D printing, life support systems, and advanced robotics are all key components of this endeavor. The Artemis program will provide invaluable data on how humans can live and work in space for extended periods, information that will be crucial for the success of Mars missions. He said artificial intelligence and automation. Artificial intelligence, AI, and automation are becoming increasingly important in space exploration. AI is being used in a variety of ways, from autonomous navigation of spacecraft to decision-making processes in robotic missions. In missions to distant planets, AI allows spacecraft to operate independently, selecting sites for exploration and conducting analyses without needing constant communication with Earth. For example, NASA's Perseverance rover uses AI algorithms to analyze images and select rock samples for study. It also has the ability to make decisions on the best route to take, avoiding obstacles in its path. As AI continues to evolve, it will play an even more significant role in future space exploration, especially in deep space missions where real-time communication with Earth may not be feasible due to the vast distances involved. The future of space travel, reusable spacecraft and beyond. One of the most promising developments in space technology is the creation of reusable spacecraft. Traditional rockets are used only once, but companies like SpaceX are pioneering the concept of reusability with the Falcon 9 rocket. This revolutionary innovation drastically reduces the cost of space travel, making it more accessible for both governmental space agencies and private enterprises. Starship, SpaceX's next-generation spacecraft, is designed to be fully reusable and capable of carrying both crew and cargo to the Moon, Mars, and beyond. Once operational, Starship is expected to transform the economics of space travel and enable the large-scale colonization of other planets, including Mars. The development of space tourism is another exciting frontier in space exploration. Companies like Blue Origin and Virgin Galactic are working on spacecraft designed to take paying customers on suborbital flights into space. While still in its infancy, space tourism could help fuel further advancements in space technology and broaden public interest in space exploration. Conclusion. The vastness of space is an awe-inspiring reminder of the uncharted territories that lie beyond the stars. Throughout history, humanity's journey into the cosmos has been marked by our relentless pursuit of knowledge and our desire to understand the very fabric of existence. However, as we venture deeper into the universe, we are confronted with more questions than answers, more mysteries than certainties. Our journey has led us to encounter phenomena that defy traditional explanations and challenge the very laws of physics as we understand them. From the invisible yet ever-present influence of unseen matter, to the inexplicable forces driving the accelerated expansion of the universe. The mysteries of dark forces and unseen dimensions are integral to our quest for understanding. It is these anomalies, these unexpected and often perplexing phenomena, that have not only advanced our knowledge, but also pushed the limits of our imagination. As we explore further, we come across objects and events that stir both wonder and confusion. The presence of vast cosmic structures that seem to behave in ways that contradict established scientific theories reveals the complexities of the universe that still elude us. Gravitational forces, often unnoticed, steer the motion of galaxies and entire clusters, hinting at the existence of forces beyond our comprehension. Gravity such as the black hole proves exquisitely present for some objects, yet brings us no closer to explaining their shiny patterns and bizarre arrangements. As we explore further, we come across gravitational forces, often unnoticed, to still the motion of the galaxy. While much of the universe remains beyond our reach, the technology at our disposal continues to evolve, providing us with new insights into the nature of space itself. Among the most perplexing anomalies is the phenomenon of the unseen matter that seems to dominate the cosmos. The discovery of forces so powerful that they manipulate the fabric of space-time, influencing the movement of galaxies without ever being directly observed, has shaken the foundations of physics. We've come to realize that the universe we perceive, with its stars, planets, and galaxies, is only a small fraction of a much larger reality. The very structure of the universe is governed by forces that, though invisible, exert an undeniable influence. The forces that govern the cosmos are far more intricate than we ever imagined, often behaving in ways that challenge conventional wisdom. The accelerating expansion of the universe, once thought to be a stable and predictable process, now appears to be influenced by a mysterious force that continues to perplex scientists. This revelation has not only reshaped our understanding of the universe's origin, but has also forced us to reconsider the ultimate fate of everything we know. In our quest to uncover the secrets of space, we also encounter phenomena that seem to break all known rules. Objects that travel across the cosmos with speeds and trajectories that defy current theories, and others that emerge from the dark reaches of space, seem to follow paths unknown to the science that guides us. Some of these objects behave in ways that suggest they might not even be bound by the same cosmic rules that govern our own solar system. The discovery of objects beyond our solar system, with their strange shapes and unexplained movements, pushes the boundaries of our understanding. Could these objects be signs of extraterrestrial intelligence, or are they simply oddities within the natural order? While many answers remain elusive, the very fact that such objects exist forces us to think beyond what we know, to imagine new possibilities, and to rethink the way we perceive the universe around us. But perhaps the most fundamental question lies in the very nature of space-time itself. Theories of cosmic gateways, wormholes that could potentially allow for shortcuts through space, speak to our desire for exploration beyond the confines of our known universe. Though such theories remain speculative and without evidence, the idea that space-time could be bent and manipulated to allow faster-than-light travel provides a glimpse into the future of space exploration. As we consider the profound implications of these anomalies, we are reminded that much of what we know about the universe is still in its infancy. Our current understanding of space is just the beginning of a much larger story, one that unfolds with every new discovery. The technological advancements we've made have opened the door to an unprecedented era of exploration, but they also raise more questions than they answer. It is clear that the universe holds countless mysteries, many of which are likely to remain unsolved for generations to come. Yet it is through these very mysteries that we continue to push the boundaries of human knowledge. Each anomaly, whether it be the strange behavior of distant galaxies or the inexplicable forces driving the expansion of space, serves as a reminder that the cosmos is far more complex and unpredictable than we could have ever imagined. In the end, the pursuit of knowledge is not just about finding answers, but about embracing the unknown. The anomalies we encounter in space are not roadblocks. They are gateways to new realms of understanding. They challenge us to think in new ways, to question the very nature of reality, and to expand our minds beyond the confines of the Earth. Each anomaly is a stepping stone on the path toward a deeper understanding of the universe and our place within it. As we continue to explore the cosmos, we are reminded that there is still so much to discover. The universe, with all its wonders and complexities, is a vast and untamed frontier, and it is through the exploration of its mysteries, no matter how perplexing, that we will ultimately come to understand not only the nature of space, but the essence of existence itself. Experience carries with it a worldview that emphasizes the simplicity and the true meaning of space. Our journey into the unknown is just beginning, and the anomalies we encounter will be our guide as we venture further into the great beyond. The future will find us before dawning its looks. There is truth in prophecy and knowing thou canst control